Okay, so we're trying to find the exponential function that passes through this point. And the function is a multiple of our basic exponential function, 2 to the x function. Okay. So y equals f of x equals 8 times 2 to the x. Now let me just make up a couple of numbers here for C and A. Let's say this is 12 and 5. Okay, so y equals 5 and x equals 12. So we plug in 5 for y, 12 for x, and we get y equals a times 2 to the 12th. So 2 to the 12th takes a little bit of calculation. And that's not y, y is 5. Okay, 5 equals 8 times 2 to the 12th. 2 to the 12th is, everybody should know that's 4,096. Well, not really, but pretty easy to find that. Okay. Up here. So 5 over 4,096 equals a times 4,096 over 4,096. You know what? No, that's right. Okay, so the a equals 5 over 4,096. Thus the function is y equals f of x equals 5 over 4,096 times 2 to the x. That's what our function is. Once we get a, we just write it down. That's very straightforward. I think everybody did that correctly. Okay. Not sure about all the algebra. I didn't look at all the algebra, but everybody has the right stuff here. Okay, let's do another one. F of x is now a b to the multiplication sign. Notice a b to the x. And we have 2 points. And let's just say these 2 points are 2. Put it down here. 2, 5 here. And if that's 2, well, it's almost a little bit more. Maybe that's 5, 28. So what's the exponential function? Well, go ahead and see if you can set it up. It was in the homework. Okay, so hopefully you've done it. Let's just see how people are with this. And then we'll go over it in whatever detail is necessary. Okay, y'all did really well with this. Let's see now. At this point, y equals 5 when x equals 2. I wrote that kind of small, but I'll write the equation a little bigger. So five equals a times b to the second, right? Plugging in 5 for y. And we like this is y equals. And if I write it like this, you're welcome to put that y in there, right? So you know where y is and you know where x is. But I think you know. So anyhow, y equals 28. But x equals 5. So (28) equals a times b to the 5th. Okay? Now, how do you solve this system of equations? Well, not everybody made an attempt to solve the system, but I was content if you wrote down both equations, but some of you did. And from what I see, you're going to use the method of solving the equation for A, solving the first equation for A, and then substituting it into the second equation. And that's the method of substitution. So we'll have room here. So let's continue it. There. Okay, so let's just write down where we are. 5 equals a b squared. 28 equals a b to the 5th. This is your first equation. This is your second equation, right? I'm going to solve the first equation for a. You got 5 equals a b squared. So to solve for a, you would divide by b squared. Alternatively, you could multiply by b to the negative 2, but I'm going to divide by b squared. It's the same thing, because b to the negative 2 is 1 over b squared. Okay, so we're going to get this. So a equals 5 over b squared. Because b squared divided by b squared is 1. That just gives you 1 times a. 5 over b squared. So there we have it. Now, we substitute the solution into the second equation. (28) equals a b to the 5th. So 28 equals 5 over b squared. Times b to the 5th. Well, b to the 5th over b squared is b cubed. If you understand the laws of exponents, and if you don't, email me. I'll tell you where to look for something to review. Okay? So you get 28. Equals 5b cubed. So the b cubed, divide both sides by 5. We're trying to isolate b. And this 5b cubed over 5 is just b cubed. Okay. Now, how do we solve this for b? Well, we raise b cubed to the 1/3. Because when you do a power with power, you multiply the exponents. Now, 28/5 is 5.6. Okay. So you can just plug that into your calculator. 28/5 raised to the 1/3 power. Okay. If you don't know how to do that, go ask Mark or bring your calculator with me and I'll show you. Okay. Just have your calculator out and show you how to punch it in. It's different for different calculators. Anyhow, b is the 1/3 power of that, which means b is the number you would cube in order to get 5.6. Okay. Now, if you cube 2, you get 8. So b is going to be less than 8. If you cube 1, you get 1. So b is going to be bigger than 1. It'll be between 1 and 8. You got your x cubed curve. It's pretty steep. You can actually estimate this if you just draw your x cubed curve. Here's 8. Here's 4. Here's 2. Here's 1. Here's 1/2, and here's 1/4. So we get a graph. Looks like this. If this graph is reasonably accurate, what number do we cube to get 28/5, which is 5.6? Here's 8, here's 4, here's 6, here's 5. So 5.6 is about here. And if we project that down, we get something pretty close to 1.8. Now I can kind of cube 1.8 in my head. 1.8 squared is 3.24. Okay. And that's a little bigger than 3. And 3 times 1.8 is 5.4. So it's going to be a little bigger than 5.4. So I think 1.8 is a pretty good estimate. So you don't have to know how to do that unless I ask, and I could easily ask. Could easily ask you to graph the x cubed function and tell me what the solution to the equation x cubed equals 5.6 is. Okay? Because we did that at the very beginning of the semester, so you might want to kind of keep that in mind. In any case, the calculator has a bunch of little graphs in it that goes to the graph and does it more accurate interpretation, right? Believe me? Just believe me. Okay. No, your calculator does it numerically. And I could explain how, but you'd have to know calculus and Taylor series and stuff to do that. Okay. So we're not going to do that. So I'm going to say anyhow that b is approximately 1.8. Now, if you plug this into your calculator, you're going to get something kind of close to 1.8. It'll probably round off to 1.8. Might be 1.7 something, might be 1.8 something. It's probably going to be between 1.75 and 1.85. I think. Just from the estimate I made and then the mental calculation I made cubing this, I think it's going to be like 1.77 or something like that. Okay, so I got to anyhow, b is about 1.8. Your calculator is more accurate than this. Okay. Especially if you graph things as imprecisely like it. Okay. Now we're not done. We've got B. We got to have A, right? We want to use the value of B to find A. You know, from our first step, that is the step we made here, that A is 5 over B squared. So B equals 1.8. A equals 5 over 1.8 squared. Even easier to do with your calculator. You don't have to raise, well, yeah, you actually do have to raise 1.8 second power. Well, that would be 5 over 3.24. And I'll just say it's approximately 3.2 because we're not so precise as to need to consider that form. Okay, well, 3.2 times, well, half of 3.2 is 1.6. 1.6 and 3.2 is 4.8. So the result is just a little over 1.5. And if we go to 1.6, then we're going to have to add like 1.86. Yeah, it's pretty close to 1.6. Now, if B is actually 1.8, B is a little less than 1.8. So I kind of think if you take this to your calculator, you're probably more likely to end up with 1.5 here. But I don't expect you to do all that you have. Take your calculator, do these operations. And my best guess for these points is y equals AB to the x, and that's approximately 1.6. That's actually within close to 1.5. That's times 1.8 to the x. Now, just to put this in context, 1.8 to the x is pretty close to 2 to the x, isn't it? So the graph of 1.8 to the x will be kind of close to 2 to the x. Then you vertically stretch that by 1.6 and you get the graph of this function. And you see if the points that I specified are on the graph. So I'm just going to kind of do that just to illustrate how all this fits into the big picture. And very simply, (1.8 to the x), if this is 1, 2, 3, 4, I could have used a bigger scale, I guess, but this will work. Okay, you're going to get 1.8 when x is 1. So you're going to have a point where y equals 1.8. And 1.8 to the x, 1.8 to the 0 is 0. I need a number to the 0 is 0. 1.8 squared, I said, was about 3.2. So this line, y equals 3.2. We could say 3.24. So the graph is kind of looking like this, as opposed to the 2 to the x graph that would go through here and here. worth understanding in terms of the graphs and so forth. Now, if we vertically stretch it by factor 1.6, then this is going to become 1.6 times as far from the x-axis, which will be a little less than twice as far, it'll be maybe about here. Okay. And we vertically stretch this by 1.6, and probably add this much to it. It goes about here. So the graph might look like this. Not a very good graph. Oh, I screwed it up. There's a reason it's not a very good graph. I didn't vertically stretch this point. So let's get that. Okay. So this point goes about here. This point goes up, I said, about here. And this point goes up to like 1.6. And now it's got more of the exponential curvature. Chalk is kind of sticking. So the graph isn't quite as pretty as I would have made it. It wouldn't have been that great anyhow. Okay, so there it is. Now, we said when x equals 2, y should equal 5, right? So let's just do an honest estimate. When x is 2, right there's what y should be, right? Does that look like 5? Yeah. This interval looks a little bigger than this one, but quite a bit bigger than this one. Not great, but plausible that this is the 0.25, right? So this point and this fits into everything we should understand about these basic functions. Okay? We just modify the 2 to the x function to get a 1.8 to the x function, which might involve a little bit of multiplication. So draw the graph, vertically stretch it. And there we go. Okay. And you should be kind of good at doing that in your pre-calculus course. That would be a reasonable question to ask on a final. You know, construct the graph of 1.6 times 1.8 to the x by constructing the graph of 1.8 to the x and doing a vertical stretch. And then estimate it there. Now, that would be the kind of thing I'd put in a final in my course. I'm not sure about anybody else's course. And I don't know why this thing does it, but it zooms. Maybe it's because we're using Zoom. I don't think that's it. Zooms itself back. So if you weren't able to read everything, my apologies. You're apologizing for the camera, but I can also apologize for not having those. Okay, there we have it. Okay, well, if you know that much about exponential functions at this point, you got a fairly good start. Okay, but there's quite a bit more that we can do. So let's take a look at it. In general, an exponential function is a vertically vertically and horizontally shifted vertically stretched horizontally compressed. Basic. Exponential function. That means a general exponential function. Now, the definition of an exponential function depends on the author you're reading. I'm not sure about Larson. He's one of my favorite authors. I use one of his textbooks in linear algebra. Okay, great technique, great author. There's actually a pre-calculus text that I prefer to his, but it's close. This would be a close second. And I love his linear algebra book and almost everything else he's ever written. Okay, so great author. I'm not sure though what he does if he defines an exponential function just as a function of form y equals ab to the x. Okay. Or if he allows you to raise it, lower it, reflect it, and so forth. In my thinking, I kind of go with the definition I believe of the math uses, okay, which is this one. Doesn't really matter if your author doesn't want to call this an exponential function. Well, then it's a vertically shifted, horizontally shifted, vertically stretched, horizontally compressed exponential function. Okay, it's the same thing. So the terminology doesn't matter that much. I could flip this board, but I don't want to keep that. So, taking off on what we've seen here, I can say that I'll call it the general exponential function. Could be written as y equals ab to the kx. It turns out that horizontal shifting can be accommodated by the way you vertically stretch and shift it and so forth. So I'm going to cross out the horizontally shifted. If you included horizontally shifted, then you have ab to the k times the quantity x minus h. Oh, now I want to change my variable here because I didn't do vertical shift. I'm going to use r in front of x, and then I'll use k for the vertical shift. Okay. If you replace x by x minus h, well, then you can use the rules of exponents, and all that does is changes your value of a. Okay. And I'm not going to go through the details of that, but that's why I cross out the horizontally shifted. The vertical stretch accommodates any horizontal shift. I could illustrate that, but I'm not going to digress. Okay, so there's your general exponential function. This is y equals b to the x. Horizontally compressed, horizontally compressed by factor r, or factor r. vertically stretched by factor A. Then vertically shifted K units. And remember, you want to do your stretches and compressions, which multiply things. Before you do like a vertical shift. So it ends up like this. Obviously, what you get if you horizontally compress is just V to the Rx. Then vertically stretch, you multiply that by A. Then vertically shift, you add K. And the way that looks depends on how much you're stretching and shifting. So this is an example. Yeah. I want to stretch it horizontally. And I'll demonstrate how that works. I'm going to do this. I'm going to vertically stretch it by factor 1.5, horizontally stretch it by factor 5, vertically shift it -6 units. So here we go. So I'm going to put 8 here, 4 here, 2 here, 1 here, 1/2, 1/4 here. And 6 will go here, 10 will go here, and 12 will go here. And down here, I'll have -6. -2 and -4. So that's reasonably a scale. Yeah, my -6 is a little big, but we're going to just live with it, okay? Actually, let me fix that. That looks more like -8. You kind of do want to have a decent scale. So then -4 would be like here. -6 here. -2. Okay. Now our graph of the 2 to the x function goes from this point, and let's say I'm going to put 1 here, and I'm going to put 2 here because of what I'm going to do later, which is horizontally stretch it by factor 5. So this is going to be 1. This is going to be 2. I have -1 here, -2 here. So you're going to have points like down here, 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 and here. I said I'm just going to vertically stretch my factor at 1.5. I've drawn this graph. That I can actually do a bigger vertical stretch. It'll be a better illustration. So I've got a vertical stretch by factor 2.5. Okay, well, there are my points. And if you want, there's my graph of the basic function. And of course, extend basic function does what it does. I'm just going to do this much because it'll be enough. I make each point 2.5 times as far from the x-axis. So I vertically stretch. How far is this? 4. 4 times 2.5 is 10. So this point goes up here to y equals 10. Now it's 2.5 times as far from the x-axis. Vertically stretch this, meaning I multiply the y value by 1.5, which moves the point, again, 2.5 times as far from the axis. We were at 2, so we got to end up at 5. One, we'll go to 2.5. Well, there's 2, there's 3, so there's 2.5. And 2.5 times 1/2 is this. 2.5 times this is this. So here's a graph with the vertical stretch. So this graph is y equals 2 to the x. This graph is y equals 2.5 times 2 to the x. Now we horizontally stretch. It's easy to do that. That means we just move every point 5 times as far from the y-axis. I have to change my chalk around. Okay. So this point is this far from the y-axis, which is 2 units from the y-axis, directly above x equals 2. So it's going to go up to x equals 10. 5 times the 2 here gives us 10. So we've got to go all the way out to 10. So let's see, if this is 2, here's 4, 6, 8, 10. 10 all the way out here. Give myself enough room. But here's 10. Here's 8. Cut that in half. Here's 4. So here's 3. Here's 6. Here's 5. Here's 7. Looks like it's really well divided. Okay, so this point has to move. That's green chalk here. That's all right. We'll use this. This point has to move all the way out here. And this point has to move 5 times as far from the y-axis. How far is it from the y-axis? Well, it's the point that we got when we shifted the point 1, 1 or 1, 2. So the x-coordinate is 1, so it must be 1 unit from the y-axis. Well, the x-coordinate is going to be multiplied by 5. That's going to move us out to. So this is going to move out and end up horizontally from here. There we have it. Okay. Now this point on the x-axis or the y-axis is on the y-axis, so 5 times as far from the y-axis doesn't move it at all. This point moves over about here, and this point moves over here. We're not going to worry too much about those points. We just know that they're going to get really close to the y-axis, the x-axis. So my x from y. Oh man, I looked at the wrong point. And then for this point, keeps curving up, but now we've extended it way out. And this will be y equals 2.5 times 2 to the 1/5 x. Why 1/5? Well, just to see that it works, when x equals 10, 1/5 of x is 2, right? Okay, so when x equals 10, this should be 2 times 2 to the 1/5 x, which is 2 to the second, which is 4. Right? 2.5 times 4 is 10, so that works. So for one reason, it's 1/5 is it works. The other reason is that we're horizontally stretching this thing rather than compressing. Okay, so I'm going to make a little note. The stretch factor is 5. So the compression factor is 1/5. And this is your horizontal compression factor. Compressed by factor R, that's where the compression factor goes. So compression factor less than 1 stretches out your basic function. A compression factor of more than 1, like a compression factor of 2, well, that's going to move everything twice as close to the y-axis. So a compression factor of 1/5 stretches you 5 times. So you can see this is stretched out 5 times as long, right? Okay. Well, then what do? We vertically shift k units. Now, you say the vertical shift is -6 units. If we vertically shift -6 units, and I really do need a different color. Okay. Then we have to take every point of this graph and move it 6 units, -6 units in the vertical direction. So when we're at 10 here, we move -6, we go down to 4. That's going to put us here. We go down, or we move vertically -6 units. And we move this point vertically -6 units. Well, the quarter of this point was 5, so we're going to move it down here so it becomes -1. We'll have a point about there. It's actually a little higher than that. This point has to go down 6 units, which means it's going to go down to here. And these points go down 6 units. Meaning that they, since they're really close to the x-axis, which is where y equals 0, they're going to end up really close to the line y equals -6, which will then be an asymptote. So we have these 2 points that are increasingly close to the line y equals -6. And we can connect these. And we get a graph. This is just pretty much parallel to this one. Same shape, just down lower. And this is y equals 2.5 times 2 to the 1/5 x minus 6. Okay, makes sense? Hopefully it does, because that's your picture of transformations. And they're pretty important for exponential functions. Now, we haven't talked about horizontal compression, but you've seen it in your homework. Okay? And it works just like I said it works. Whatever your horizontal compression is, it's bigger than 1, it moves things closer to the y-axis by that factor. If it's less than 1, then it moves things further away. Okay, let's try an exercise here. Okay, 3 exponential functions. How do we graph them? Okay, now a lot of people are wanting to make tables and graph from tables. Okay. What we're trying to do is we're trying to see how the transformations work. And if you're going to make a table, that's okay for right now. Just going to extend this. If you're going to graph by transformations, you start with the table for your basic function and draw the graph. Okay, so that's automatic. You want to do that. Then, once you have the table, you don't have to go to that much trouble to evaluate 3 times 2 to the x because you've already got 2 to the x. So you multiply these values all by 3. And of course, that's going to make the y values all 3 times as big, which is going to move your points 3 times as far from the x-axis. In any case, you multiply these by 3, so you get 3 times 1/4. Automatically, 3 times 1/2 is 3/2, which is 1 1/2. 3 times 1 is, anybody want to hold up fingers for that? Well, I know that's 3. 3 times 2 is 6, 3 times 4 is 12. So if you want 3 times 2 to the x, you just do this, okay? But you always want to start with your basic tables. All right. Now, when you graph these, when you graph this function, you want to first, just like I did, have the graph of 2 to the x here so you can see how they compare. This graph was 2.5 times 2 to the x. What do you think 3 times 2 to the x is going to look like? Well, 3 times 2 to the x is a little bigger than 2.5 times 2 to the x. It's going to be a little higher than this graph. So that's what it's going to end up looking like. Now 2 to the 3x and 2 to the x plus 3 won't look much like anything you've already seen. But you want to imitate what I did when I drew these graphs. And if you want to use a table, for now, that's okay. Okay, now I was a little sneaky. I did 3 times 2 to the x, so the graph would look like what you're used to. So of course, I said negative 3 times 2 to the x. What's that mean? Well, all the values would just be the negatives of what you have here, right? Okay. I recommend that you finish these, but right now, I'm going to show you what comes from what we have here because we're almost out of time. So, as it turns out, we can use a fairly broad scale. And I can put it's 16 up here, so it'll be down here 4, 12. Then you got 2, 1, and 3, 1/2 and 1/4, and 5. I mean 6 and 7 and 5 and so forth. Okay. Get your scale and you sketch your points for the y equals x squared function. That y equals 2 to the x. And it looks kind of like this. Because I'm using a lot of fairly big numbers up here, the graph looks a little flatter than usual. Now, I multiply all my y values by 3. Okay, so instead of the point 0, 1, I get the point 0, 3. Instead of the point 1, 2, I get the point 1, 6, which will be up here. Instead of the point 2, 4, I get 2, 12, which is up here. So these points, they kind of close to the axis. Not drawing them exactly because it's a little tough to do that by hand with a piece of chalk. So we can pretty well see that we've taken this x squared or 2 to the x graph and stretched it by a factor of 3. Stretch everything 3 times as far from the x-axis because all these y values are 3 times as big. Now, if we want -3 times 2 to the x, so that's going to make all these numbers negative. So what's going to happen? The 12 is going to become a -12. So let's see that. 8 is about there. A -12 will be about here. So that 12 is going to become -12. That's going to put us down here. When x is 2, y is now going to be -12. So what that did, you can see from the numbers, that flips this point on the other side of the x-axis. And it does the same thing for this point. Which will put it down about here. And for this point, which will put it down, oh man. I didn't draw this graph quite right. Let me fix it. It should be at 6 here. Here. That's more like this anyhow. Okay. So we flip this point down here. And we flip this point down here. And we flip this point down here. And there we got our graph. Okay. For the 2 to the x plus 3, of course, we're going to go back to our 2 to the x values and just add 3, right? So we say that's okay, that's 3 and a 4. 3.5, 4, 5, and okay. And what we're going to see is it's just going to take the 2 to the x graph, which is here, just going to lift it up 3 units. Every point's going to move the same distance, unlike from here to here, where the points that have bigger y coordinates move further than the points that have smaller y coordinates.